All right, well, I think I'll kick things off here. So welcome to those of you joining here in person at the Wisconsin Energy Institute, and welcome to those joining online. This is the Sustainable Energy Seminar Series. It's also a class called Engineering Physics 418, Sustainable Energy Challenges and Solutions. My name is Scott Williams. I'm the instructor for the course and the organizer of the seminar series. I'm also the Research and Education Coordinator at the Wisconsin Energy Institute. So I help to lead energy education efforts both for students here as well as the public. And the Sustainable Energy Seminar, it's a program that we hold every other week, every other Monday in the fall and the spring semesters. And our goal is to highlight the cutting energy research that's going on from across UW-Madison and showcase how different disciplines understand sustainable energy challenges and develop solutions. Throughout the series, we'll hear from folks in science and engineering, as well as social sciences and humanities, to learn about the ways in which they view sustainable energy challenges and solutions. The seminar is also open to the public. You're welcome to join here in person at the Wisconsin Energy Institute or online through the Zoom webinar. It's also, again, a course for students in the undergraduate Engineering for Energy Sustainability certificate, as well as the Master's in Sustainable Systems Engineering. You'll notice this hybrid format. I'll try to read out the questions for those who have questions online. I'll make sure to be monitoring both the chat and the Q&A. For those in the room, if you have a question, I'll ask our presenter to repeat it so that our online folks can hear it. And also, if I can also hand you a mic if that helps, if that makes it easier. We do have live captioning available. I'll turn that on quick if folks online would like to show the captions. I'll make sure those are not on the screen here. Okay. So if you do need live captioning on Zoom, I've got that feature turned on now. And again, please use the Q&A if you're joining online, and I'll direct that to our guest presenter today. So our guest speaker kicking things off the spring semester is Yiying Zhang. She's the Associate Director of the Great Lakes Bioenergy Research Center, which is part of the Wisconsin Energy Institute here. She joined GLBRC in 2021, and her position is supporting the GLBRC Director and management of the Research Center, which includes strategic planning, business operations, staff management, research program development, and stakeholder engagement. And before that, she brings 20 years of experience in business strategy and program management in renewable energy and sustainability sectors. And she has led nearly 100 renewable energy projects in 20 countries on 6 continents, primarily in hydropower, which she'll be talking more about today in her presentation on hydropower, pump storage, and the fight on climate change. Welcome.
Thank you, Scott. Thanks everyone for coming today. I'll have little questions along the way. So for those of you who are in the room, if you know the answer, just yell out. Those of you who are online, feel free to type your answer in the chat if you want to, and Scott will help me read those chat messages. So let's get it started. So today I'm going to talk about hydropower and pump storage and how we can leverage hydropower and pump storage to help with the energy transition and fight climate change. So this clicker's not working. I'm going to use this. What's going on here? There. Can anyone tell me what is the largest hydropower project in the world? If you had paid attention to the last slide, you would have already had the answer. And apparently the ones in the room did not. And nothing online either, is there? Okay, that's fine. Three Gorges. Okay, you got it, Three Gorges, okay? So this dam is the largest dam in the world right now. And the project is also, the capacity is 22.5 gigawatts. Remember that number. That's the world's largest hydropower project right now. Okay, the next one. What's the largest hydropower project in the US? Hoover. It's a big dam, but not the largest hydropower. Good try. Anything online?
Not yet.
All right, I'm gonna give you the answer. It's Grand Coulee. So Tennessee is a big portfolio, but a single hydro project wise, Grand Coulee's largest, 6.5 gigawatt. And that's close to 1/3 of the largest hydropower in the world. And a fun fact about me, I worked on both projects a little bit. All right, so today I'm gonna talk about a few different topics. The first half of the presentation, I'm gonna go over some basics and some fun facts about hydropower and pump storage. I understand most of you don't have that expertise, so I want to give you some backdrop. Then we're gonna go into how climate change is going to impact hydropower and how hydropower is going to impact climate change. And then we'll talk a little bit about food, energy, water nexus, and then we move into more of the ecosystem of renewable energy, just a little bit. So hydropower, fun fact, the first hydropower was actually built right in Wisconsin on the Fox River. Tiny little thing that can only generate enough electricity for 2 homes. But it was built 140 years ago, so pretty impressive, right? And it's still standing. I believe the dam is actually there. So the types of hydropower, the first one is what you see the most common. It's the traditional conventional hydropower. As you can see, hydropower basically consists of a dam, and then you have a reservoir that has higher water elevation, and then you have the river on the tail race side. And there's a head differential between the two, and the water picks up velocity as it runs through the channel of the dam. So it picks up velocity, and the velocity will turn the turbine in the powerhouse, and that gets converted into electricity through the generator, and then it goes into the substation and transmission system and go into the power grid. So that's kind of in a nutshell how things work here. And then one of you mentioned Hoover Dam. So there's 2 subcategories of hydropower. One is called impoundment or storage dams. And this one, basically you have a large hydropower, large reservoir behind the dam that stores a lot of water, and normally it has a pretty high head. So it stores that static energy in there. When you need it, it will release the water, and it's going to flow and generate electricity. A lot of times, because there's a large reservoir, it actually serves multiple purposes beyond just hydropower production. It also uses for flood control, because you could store water when you have a big rainfall event, so it doesn't flood downstream houses. And also some of them are used for irrigation, right? So in dry places like California, you can store a lot of water during the spring when the snow melts from the mountains. And then in the summer, when you are dry and you need water the most for crop, you can release more water through the different channels, right? So normally those kind of projects are multi-purposes. Now the second category is called run-of-river. Run-of-river projects are normally much, much smaller, and it does not create a large reservoir. Some of them you can't even really tell if there's a reservoir. And the water is diverted through a channel and then send it through the turbine and generator in the powerhouse. And the name run-of-river basically means whatever water comes into the upstream of the dam would have to go out in the downstream of the dam. So it's the same flow volume that comes in and goes out. So it does not have the capacity to store extra water in the reservoir, because you can do the math, right? What comes in goes out. So it does not have the extra capacity that functions as the other style. But it is more environmentally friendly. It is easier to construct. So you're gonna see a lot of those in the US and around us. The second type of hydropower is pump storage. So pump storage works very similarly as the traditional hydropower. It has basically utilized the differential head between the upper reservoir and lower reservoir. So the difference is that it's not going through the traditional, like the traditional dam basically follows the alignment of the river. The reservoir is on the upstream side of the dam, and then the tailwater is on the downstream side of the dam. It's on the same river. But for pump storage, normally the upper reservoir is actually in a separate location. You can kind of see on the schematics on the 2 pictures on the right, the upper reservoir is off on the side. And then the lower reservoir can be either a standalone reservoir, or it could be actually the active river. So if the lower reservoir is a reservoir disconnected from the river, then it's called closed loop. So closed loop means the basically the circulation between the lower reservoir and upper reservoir is closed. It's not exchanging water with the natural river. But when the lower reservoir is the actual active river, it's called the open loop system. Now, the cool thing about pump storage is that when you need energy, you can release water from the upper reservoir. Then it generates energy just like any other hydropower. But when you have too much energy in the system, you don't need to generate extra energy, then this system is reversed. Then you pump water from the lower reservoir to upper reservoir. So it's basically a gigantic battery there, right? It can sit there until we need it. But there is energy loss in between because when you are pumping, you're using energy, right? Now, the next type, I kind of merged everything together. It's more of the emerging technologies, marine energy. We're not going to talk a lot about those, but those are basically using the other types of dynamic motions in the ocean or in the river, and or even thermodynamics to try to generate energy. They're not quite up to the industry scale yet, but some of them are. But that's not what we want to cover too much today. Now, next one, we'll talk about just the different capacities by countries of hydropower. As you can see, China, United States, Canada, Brazil, they're all leading the charge here. And you can see that China, even though it's about 16% of the power consumption in China is all powered by hydropower. Brazil is actually about 70%. Brazil is one of the leading countries for hydropower. And the United States, even though we're the third in terms of capacity goes, is only about 6% of energy that's produced by hydropower. Now, I want to point out one other country, Norway. It is kind of on the lower rankings because it's a smaller country. However, 97% of all energy generation in Norway are hydropower. So they're one of the most advanced in the world in terms of using hydropower. So different benefits of hydropower, as some of you probably already know, hydropower is very available. You have water in many different places. Whenever you have water, you have that potential for hydropower, right? So if you look at the energy generation, now we're talking about electricity generation. We don't touch on the fuel side or the heat side, but if you just look at the electricity generation, hydropower is about 15% of all energy sources. But out of all the renewable energy, hydropower is somewhere between 50 and 60%. So it's a pretty substantial component of renewable energy portfolio. Next one, hydropower is reliable, flexible, water is flowing all the time, right? Unlike wind and solar, when you don't have a control, and it varies from day to day, hour to hour, season to season, you have a relatively steady availability of water flows. Now, you can argue that there are droughts and there are flooding. Yes, there is variation. We're going to talk about that and talk about how that impacts the hydropower generation and operations. But hydropower also has this ability to ramp up very quickly because you have water, especially for those projects where there's storage right behind the dam, or pump storage. You have the upper reservoir. You have the water there readily available. You can send water down when you need it right away, and instantaneously it can start generating electricity. And that's something that wind or solar cannot do, right? Right now we rely a lot on fossil fuel plants because you can burn coal right away. You can activate that very soon. But hydropower serves very similar functionality in that regard. And then also when you have wind and solar, as I mentioned, it's very intermittent. It varies and you can control. But hydropower, you have some capability to control that, especially when you have pump storage and hydropower. You can try to time when to produce, how much to produce for some of the hydropower capable plants. And also hydropower, some of you probably have heard, well, it takes a lot to build a hydropower. Yes, the upfront cost is very high because it has infrastructure. You have to build the powerhouse, you have to build the dam, and you have to get all the permits and licenses. However, hydropower lasts much longer than a lot of the renewable energy projects you know, for a solar project, you have to recycle it probably in about 20 years, or maybe 30 if the technology is better. But also efficiency reduces as basically year by year, right? About, I think for solar, it's about 0.6%, if I'm right. But hydropower, you see dams been standing there for over 100 years. And you can basically continue to run those projects. You may have to do some maintenance, you have to do some upgrades, but as long as the infrastructure is still there, you can continue to use it. Their the Prairie du Sac Dam, right in Wisconsin, that was built in 1912, so it's 111 years old, and it's still running really well. And the cost obviously will depend on where you are in this world. In the US, labor cost is really high, so when you do construction, the cost is much, much higher. But in Africa, Asia, where labors are cheaper, you can have a much lower cost. And if you look at the overall lifetime cost of hydropower, it's one of the lowest compared to other energy sources. Obviously, hydropower is relatively clean. It's not 100% carbon-free. No energy sources is, right? But hydro is one of the lowest in terms of CO2 emission, and we'll talk a little bit more about that later. Flood control, as obvious, we talked about that. Actually, the picture on the left was a picture from my hometown. And I used to live right behind that building, right there. And I remember for 3 months, every summer, that was before Three Gorges Dam was built. By the way, my hometown is in the upstream, in the reservoir of Three Gorges Dam. Every summer, at least for 3 months, the people who live in those buildings, you can see, those buildings are in water. They can't live there. They actually physically had to move to a different place, live on the street, on the side of the street, in the alleys for 3 months. And so if anybody argue the benefits of Three Gorges Dam, I would say it's not hydropower, it's flood control. And I don't want these people to have to move out every year for 3 months anymore. So that's the biggest benefit of some of these flood control projects. Next, job creation, obviously. If some of you read history during the Great Depression, part of the reason that they built Hoover Dam was to create jobs. They create 20,000 jobs for the construction. So there's a job creation. And now with all the maintenance and the operations and licensing, permitting, engineering, whatever, hydropower can employ a huge number of people. And for those of you who are maybe want to explore what you want to do in the future, there are many, many different opportunities in hydropower, not just engineering. You can do many different things in this industry. And there's a projection, basically, the job creation will go up by more than 50% by 2050. Recreation, obviously, we all know, we go fishing. You know, that's why the lake properties are so expensive, right? And you can go whitewater rafting in the water. So there's all kinds of benefits there. Now, done with benefits, let's talk about adverse impacts. I think the biggest dispute we have heard about hydropower is the impact on fish, on salmon, on Columbia River. And here's a kind of a schematic about how hydropower industry has addressed a lot of that problem by building fish passage, building those, we call that step pool on the left side. That's a step pool where fish has those smaller pools where they are able to jump a small distance and they can go up that way. The picture on the right is the actual picture I took at Rocky Reach Dam on the Columbia River. It's actually, so you can see this is the upstream pool. And then the pipe over there is actually the downstream passage. Oh, I'm sorry. The downstream passage where the fish from upstream can go through kind of like a water slide. It's a little bit mild water slide, but it's a really long one, and go there and then get to the end of the pipe, they basically drop into the river. And I was involved in designing a few of those, not this one, but some other ones. Cultural resources. Again, those pictures are actually things that are actually from my hometown when the Three Gorges Dam was built. Those are the same one, but the one on the left is before the Three Gorges Dam was built. It was on the high mountains, really tall temple. I went there, really loved it. Then when the reservoir was built, it was 300 feet deeper water. After the reservoir was filled, it became kind of a little plant in the middle of the water. And they, to protect this, this landmark, Chinese government built this wall in the middle of the river to preserve that, that piece of history. But there are a lot of buildings, historical buildings and things that were actually underwater now, unfortunately. Relocation, we heard a lot about immigration. The Three Gorges Dam relocated 1.1 million people, including my house. I used to show you where I lived before. That was right along the river. And that building is no longer there. It's way underwater or demolished. We had to move uptown by hundreds of meters higher. So that's definitely one of the side effects from building the dam. Any questions about hydropower so far? I just want to give people the opportunity. You don't see anything online? All right, we can move on to pump storage. So we talked about kind of in general how pump storage work earlier, so I'm not gonna repeat that, but you can see pump storage basically takes a pretty large footprint. They're usually built on mountains, and a lot of times the differential elevation between the upper reservoir and lower reservoir could be over 1,000 feet. So it's a large footprint, but it's a gigantic battery essentially. So you compare that with a battery system bank, it's similar, but this is probably much, much smaller footprint. But the capacity of those two are also very, very different. So we'll get to that in a little bit. So on this slide, you can see, so for a battery storage, theoretically, you can basically put as many batteries as you want in the building, right? If land is not a problem, you can put unlimited number of batteries to increase the capacity that it can store. However, the cost of that and also other associated problems, risks or fire hazards, whatever, would increase, and cost would also increase because of the infrastructure and land acquisition costs and whatnot, and technology requirements. Now for pump storage, it's the reversed situation. So when you build a small pump storage, because of the need for infrastructure, the cost per kilowatt or megawatt is much higher. You can say started pretty high there, right? That's the blue line there. And then for battery, it's pretty steady because it's more linear, like per unit kind of. But it doesn't count for the risks and other costs, in my opinion. But pump storage, when you get to a much bigger capacity, when you need to be able to generate energy, for example, for a day or a week after you have a blackout, the cost per unit is much lower because the infrastructure is already there. The increase in cost to build a bigger infrastructure compared to a smaller infrastructure is not as big. So there's a little bit of that comparison there. Now, as much as we talk about battery storage, the reality is most of the capacity in storage, energy storage, is actually pump storage instead of battery. As you can imagine, because the pump storage can, it has typically have much larger installed capacity than batteries can do. So currently 95% of the energy storage are in pump storage form, and the other 5% is various types of technologies, including the battery storage. Benefits of pump storage, I'm gonna just go through this relatively quickly. We can store energy, as we talked about, this gigantic battery. It can generate energy when we need it. And when you have a blackout, when you have a power outage, it can instantly send water downstream and start generating. So we call that black start capability. And also we can manipulate when and how much we generate power depending on the demand and the energy supply at different time of the day, it provides that stability to the power grid. Also stores water in the reservoir, obviously, and also can help arbitrage some of the flows because of that water storage there. So talking about the grid, the energy storage here. So I have an example here. So this is, it's called duck curve. As you can see, the curve looks like a duck. And this is basically showing in California, you can see through the day, the energy demand. So all of these lines are energy demand, net energy demand, subtract out the supplies. So during the day, when in the morning, everybody's getting ready for work, you have a little peak of that demand. That's when you need a lot of energy, right? And during the day, you have sunlight and people are not at home, they're not cooking. So your energy demand is much lower. But that's when the sun is out the most. So you're generating the most energy through solar power, but you're not using a lot of energy. So the net between the two, the difference between the two gets larger and larger as you build more solar. So you can see in 2019, the dip is not as big. And then by the time you get to 2021, the dip is much higher because there's much more solar generation. Then what do we do? And this is not good because when you have that big of a variation, the power grid, the transmission system gets more stressed out because there's so much oscillation in the system, right? And then also when it gets to evening time, sun is down, you start producing less solar power and likely less wind power as well. But everybody's home, they start cooking, they start using the lights and start doing laundry. Then your demand skyrockets, and then, but your supply is not keeping up. So that's when we need storage, whether it's pump storage or battery storage in some shape or form, right? Then we can start producing energy in the morning, at night, and then storing energy during the day. So who has the highest pump storage capacity? China, Japan, and United States. And as a matter of fact, United States started building pump storage in 1960s. A majority of the installed capacities were built around 1970s to 1980s. We really haven't built any large pump storage since the late 1980s. And to the contrary, China and Japan didn't really start doing pump storage until about 20, 25 years ago. But within a very short span of years, because they understand the need for pump storage, they just caught up and exceeded us by far, by a lot. And we need to realize that, and we need to start building pump storage again, in my opinion, but that's a different story. All right, so any questions about pump storage? Go ahead.
You said it kind of stopped being
be constructed.
The construction of it stopped there around 1980. Is that because people stopped thinking about it, thinking on it? So is it because there are no more suitable areas? Why did it stop?
So the question, you want me to repeat? Yep. So the question is, why did the pump storage construction stop in 1980s? So it's not only pump storage that stopped in 1980s. Hydropower stopped in 1980s, more or less, because of all the environmental concerns, which in a lot of ways is valid. It's taking a lot of land. It has issues with fish, right? At that time, there was no fish passage built for these projects. So people were concerned that you're blocking out those migration paths for fish, and then there's the sedimentation issues. So a lot of concerns arose on the environmental side, and it just became kind of this big blowout, and hydropower is bad, got a lot of bad press, and that's when basically it stopped. And also there's the financial side. It costs a lot of money. The licensing permitting process got much longer, much more complicated since 40 years ago. So it's much more difficult and it takes longer to develop a hydropower. That's a real big reason. And pump storage is by far much, much higher than most of even hydropower projects of wind or solar, if you compare the order of magnitude of costs. So
we do have a question online. What is the most difficult aspect of pump storage projects? Is it finding a suitable location, permitting, construction, or something else?
it's everything and beyond. But you ask different experts, they will probably give you different answers. I always say, when money is not a subject, you can do anything. So pump storage, as I mentioned, costs a lot of money. Big pump storage will cost over $1 billion, for example, the big ones. Finding the investors, the banks that are willing to have those early investments and take on a lot of risks without knowing if the project will be approved, that's a big hazard. That's a big risk upfront. So it's very difficult. And also monetizing, kind of trying to figure out what the values are. So, you know, when you do any project, you do a cost benefit ratio analysis upfront, right? Knowing how much revenue or value your project can generate compared to how much it's going to take to build it. Now, for pump storage, a lot of these benefits I talk about, arbitrage, grid stability, storage. How do you monetize it? How do you calculate the actual number, right? Especially since we haven't built a new one in 40 years. We don't have a model to compare to what it really costs to provide that capability, which you may not need on a constant basis or ever, like black start, and that's another example. When are you gonna have those large scale power outages when you do need a black start, right? How many times have we seen the big winter storm happening in Texas? Once in our lifetime, right? And before it happens, nobody knew it would happen and nobody thought, why do I need to build something like that? So that's an example, right? So those are all realistic challenges. Go ahead.
Most of the pump storage or hydropower, for example, is basically on rivers or streams, water streams. What if we want to implement, I would say most likely a pump storage in dry land with no rivers, utilizing seawater? Has that been done before? Is it possible?
So great question. The question is, a lot of the examples I showed around active river, active waterways, have there been technologies or cases that's been evaluated on dry land, create reservoirs with seawater? I don't know exact answer. Maybe Kim has a little bit more knowledge. I know a lot of kind of off-the-wall innovative ideas have been evaluated, including underground pump storage or using other sort of media instead of water. I don't know specifically if seawater has been explored. I think it has been.
The barrage system, that's just using tidal differences though. So you capture the tide behind a barrage during high tide and then you meter it out during low tide. So that's an example of pump storage. A little different, but it's using seawater. The other newer technology right now that is just in the lab is using water banks, where you pump water into a confined space, pile dirt on top of it, that provides pressure. And therefore you can do pump storage without any elevation.
Yeah. So there are many, many different ideas out there, right? Next time if we have Kim talk, you can give him the mic so people online can hear better. But talk about dry lines, a lot of, like I said, the closed loop pump storage, for example, the reservoirs are not connected with the water, right, with the river. They're probably close enough to the water, but a lot of them, the reservoir is filled by precipitation, just rainfall on snows. So they fill slowly, but once they're filled up, there obviously has to be studies done for water balance. How fast can you replenish through just natural rainfall when you have to activate those projects? But it happens.
Do you think it's a beneficial or a very efficient way? Since like I'm thinking of my home country, Saudi Arabia, especially right now, the vision of 2030 sustainable energy and whatever. and hydropower is a big concern. But I can't really realize. I just tried to imagine hydropower implemented in a dry land with no rivers, not a lot of rainfall either.
Right.
So,
So is it feasible? So the follow-up question is it feasible in a very dry climate like that? I plan a lot of hydropower in Africa. Africa is kind of similar, it's relatively dry. In those countries, you're not gonna get large-scale hydropower like Three Gorges, even Grand Coulee Dam, but there are a lot of, microgrid, tiny hydropower or hydrokinetic. You use the little bit of a water you have, a little bit of energy you can convert. Aggregately, you can still get to a pretty substantial amount. But yeah, you're not gonna get, pump storage will be hard, but you can probably investigate, groundwater type of technologies or concrete, sand kind of storage. Yeah, that's why we're looking at a lot of different technologies. You had a question there too, right?
That was my question.
Oh, perfect. Wonderful. Great question.
A couple more questions online.
Okay.
One was, will we see a rise in hydro construction anytime soon?
I wish and I hope that happens. There has been a lot of, so I started actively doing a lot of hydropower planning back in 2005. That's when there was a lot of tax incentives and some initiatives to start hydropower again. So it's been under a lot of planning and a lot of design work. Kim and I actually built a couple of hydropower, through the pre-planning, through construction. So that's encouraging, right? So there's a lot of activities going on. You haven't seen a lot of under construction yet, mainly because of the long licensing permitting process to make sure you have minimum environmental impact, you have addressed all the socioeconomics issues, and also, you have enough financial investment. So there's a lot of activities going on. I hope we'll have a lot of actual construction going on in the next few years.
Sorry, I got a couple more here. So one, I think I was referring to this graph here. Was wondering why the capacity showed in megawatts rather than megawatt hours.
Those are installed capacity. They're not actual generations. So when you generate electricity, when you use them, you are referring them to kilowatt hours, megawatt hours. But these are installed capacity, which means you are capable of generating up to this amount. And especially for pump storage, when you have, let's say, 1,000 megawatt installed capacity, doesn't mean you are always going to generate to that full capacity. It depends on the demand. It depends on when you need it, right? So we can probably find data about how much is generated, but because pump storage has a complex benefits beyond generation, the generation itself doesn't do its justice to show the benefits.
Sure. And final online question, do you think the duck curve will have less emphasis in the US with US going more towards electrification, using more electric devices during the day, I think?
I don't know for sure. I think, with, so if we go more into electrification, there will be more demand, but how much is that going to impact the overall demand? I think it's probably a still relatively insignificant fraction, and we still have a lot of wind and solar being built. So if that speed exceeds the speed of electrification, the duck curve may get worse. So it really depends on the dynamics between the two processes.
All right.
Very good. Any more questions in this crowd here? Let's move on then. We have a lot of interesting things going on. Climate change. So let's first talk about how hydropower has an effect on climate change. When we talk about hydropower, when we talk about climate change, we talk about CO2 emission a lot. So this chart basically shows where hydropower is compared to all of the other energy sources in terms of CO2 emission. And you can see on average, hydropower is one of the lower ones, if not the lowest. We'll also be able to store some of the CO2 in the reservoir water. That's why we can actually, the reservoirs can prevent emission of CO2. That's a large, very big benefit as well. And we already talked about, the water storage and provide that flexibility, especially under changing climate where we get a lot of extreme events, droughts and flooding. So we need more flexibility and we need more ability to provide those kind of adaptive measures. And so when we talk about the climate change, we hear a lot, especially in the last 2 years, about drought in the kind of Pacific Northwest in California. But we also see a lot of flooding on the east side of the country. So really, climate change can affect hydropower in so many different ways. Some are more beneficial, some are less. So we need to look at a holistic portfolio of different factors. Water availability. When you have drought, you have less water available. When you have flooding, you have more water available. But can you utilize all of that water to generate hydropower? No, I'll talk about that in a little bit. And flow variability. When you have water coming all at once compared to steady flow for a month, that's going to affect everything as well, right? And we already kind of touched on extreme events and drought, and also temperature. When we have a lot of heat waves these days, how is that dramatic temperature going to affect the water in your reservoir and also the organics and the quality of the water in the reservoir? How does that matter, right? So we have a lot of challenges these days with water management and how to adapt to the different characteristics that we were not used to in the past. Now, this is a comparison of the heat map, a drought map from 2000 and 2022. You don't have to read everything carefully, but all you can see is how much more red is it on the right side in the matter of 20 years, right? You can see Europe is horrible. Most of Europe is under dark red, and US is, on the West Coast is much more red, and South America and Africa follow similar trend. So basically, globally, we're seeing a lot more drought than we used to. And here's the actual pictures of the Hoover Dam reservoir. 2000 on the far left side, you can see the water, very nice. And then as time goes on and you go to 2022, you see the river is much narrower. This is part of the reservoir. It's much narrower, and you see all the sandbars. It's not even sandbars anymore. You basically see the bottom of the reservoir. You see on the news, you even found cars and dead bodies and all that stuff that were never revealed in the last 60 years. And then here's another map of where all the hydropower plants were back in 2020. So that's September 2022. That's in the midst of the drought. And we can see it's very clear the hydropower plants in Pacific Northwest, especially in California region, it's under severe drought. But there's a very, very big difference regionally. On the East Coast and Midwest, it's actually not impacted as much. So that presents some unique challenges as well. So this chart on this slide shows a very clear picture of how that drought affected hydropower generation in 21, 22. So the gray curve on this curve, the top one, is basically average monthly for the last 10 years. And the dark blue is the actual monthly generation in Pacific Northwest. As you can see in the water years, the generation follows the monthly average very well. But then in 2021, in 2022 especially, the hydropower generation is much less than what it used to be historically because of the drought. And this problem is a lot more exaggerated in California, where you can see in the good years of 2017 and 2019, the hydropower was doing great, much higher than the historical average. And then 21, 22, especially, it's about almost half of where it used to be. That's a huge huge change. And the reason for that is, and let's look at the equation here a little bit. So the hydropower production is basically a function of the volume of the water and the head you have. So you have two variables here, the volume and the head. So when you have a drought, the volume is much lower. It's going to severely impact the capacity, right? And the Oroville Dam, that's the highest dam actually in the US that almost failed in 2017, that's a year. It was shut down for almost half a year. That never happened in 60 years history of that dam. And probably very rarely in the entire hydropower industry history. So in other regions, if you remember that map I showed you about drought, Eastern US was not as affected, but they were affected by actually flooding. It's the reverse problem. Now, when you think about flooding, you think about, oh, more water, more M on the, on this equation, right? But the problem is we have another variable here, which is the head. So when you have more water flowing through a dam, and on the eastern side of the United States, a lot of the dams are pretty low. They're not like the Oroville, Hoover dams. They're very low. And when you have a lot of water going through, the head is increasing on the upstream side, but it's also increasing on the downstream side. And normally it's increasing faster on the downstream side than the upstream side, which means the head differential between the two is gonna get less. So the net head is getting smaller. So because of that, you're actually generating less water, less electricity, even though you have more water. And besides, there is a lot of the projects, the dam projects on the East Coast is for flood control purposes as a primary function. So when you have to decide if you're gonna optimize the flood control versus generating electricity, you are going to have to do the flood control first, which may hurt the hydro generation. And in the Midwest, we're more diverse here. We have smaller projects, but the climate change effects have been less. We don't have severe drought. We have a little bit heat wave, and that's nothing compared to the California, right? So we are more adaptive, and the difference, the variation is a lot more different. So there's no like a huge trend, either you have too much flow or too much drought. So that balances out quite a bit for us, which is very lucky for us. In the southern US, it's very similar to California, as you can see in the previous slide here. In the south, there's pretty dry, dark red there. So they're also affected by drought quite a bit. So even though there were a lot of drought years, if you look at the yearly production of hydropower, and we pick out the drought years, that is 2001, 2021, 2022, the overall production in the country by hydropower didn't vary a whole lot, which is good news, right? Like I said earlier, one of the benefits is reliable. It's the availability of water. And if you look at the grand scheme of the whole country, even when we have bad years, we still have decent production. Here's another real example from 2022. In September, in the Pacific Northwest, they had a cold front that hit the region. And you can see the green line here on both charts. Those are production from variable energy, which is wind and solar mainly. And this, as you can see at the beginning, it produced a lot for a couple of days. And then towards the beginning of October, it went down to virtually zero because it got so cold and it brings no wind. The nuclear and fossil fuel was not impacted, but a relatively smaller capacity. So it's very steady, but it was not nearly enough to compensate for the need for energy demand, which is those red curves that's extremely high, right? And as you can see, what's matching that more or less is the hydropower. That's the blue lines. There are a lot of dams on the Columbia River. And that's what they used to compensate for that loss of variable energy. And this is an example I just snapped from LinkedIn last week. So those of you who were here 2 weeks ago, in Wisconsin, in Madison, remember that cold week that you don't want to go out, you don't want to go anywhere, it's minus 30 degrees? Unfortunately, Pacific Northwest also had this problem, super cold. And see what happened with their wind energy here. Those brown lines, it died down to 0. Same problem. But here, the blue, kind of bluish, greenish columns are the hydro production by 4 lower Snake River dams. That's at the corner of Idaho, Oregon, and Washington State. And they have produced hydropower very steadily and even increased a little bit when the wind was not producing anything. And then the lines on the top, again, similar to the slide earlier, it shows the energy demand and it shows the overall hydro production in Pacific Northwest. And again, you can see the hydro production of hydropower during that time was matching the grid requirement very well. And then here's the picture that shows hydropower actually was able to compensate for 70% of the energy production during that time when people need the most, right? You need heat in their house. So that's kind of does that give you a good idea of how hydropower works under the climate change situations? Any questions, comments? Anything online? If not, we'll continue. What time is it? I still have plenty of time. You have something?
Sorry, there is one question here.
Sure.
Are there studies that compare before and after evaporation from storage hydro plants related to water surface area? If so, does this have any negative impacts on neighboring environments?
So there definitely are studies that have been done. Actually, it's a kind of a routine thing, especially for pump storage. You have to look at your evapotranspiration. What's the rate and how much can you refill? How much can you, do you need to use, right? You have to do that water balance. And the pictures I showed you earlier about Lake Mead behind Hoover Dam, that was part of the study of looking at, okay, how much surface storage you actually lost because of the drought and how that impacts the hydropower generation. I don't think Hoover Dam actually got shut down, but it was threatened to shut down, was very, very close. And the generation was at a fraction of what it used to be. So I don't remember the numbers, but yes, there has been a lot of studies to look at the relationships between the drought, the temperature, and the loss of storage, loss of generation. And because of the rise in temperature and you have less depth of the water, it will impact, obviously, the temperature, the overall temperature in the reservoir and how that impacts microorganics and the other, another biological things, ecological things in the reservoir. I just don't have the exact example.
Okay.
All right, good. Let's move on to talk a little bit about food, energy, water nexus. So here comes another question. Who can give me examples of the relationship between food, energy, water, just between any 2 of them? You don't have to give an example between all 3 of them, but give me some examples. Agriculture, right? And specifically, how do you? Right, you need water to grow food.
Or to harvest that.
Exactly. For harvesting, you're running, machines and even for irrigation, a lot of the, automatic irrigators are hooked down to power, right? Great example. Any more? So lots of cooling water, right? So when you do energy generation, they're not only generating energy, they're also using resources. They're using a lot of water for cooling. Nuclear, same way, lots of water, right? Hydropower uses water, but the water passes through. But it changes some of that flow regime, changes the temperature a little bit. So there is a little bit of that impact also there as well. Any other answers someone can give me? Or I'll give you the answer. So there's a lot. We talked about, the food growth, but also biofuel. My organization does biofuel, and we're growing crops to produce energy, produce fuel. But then in order to grow those energy crops, you need water, you need energy. Also water distribution, desalination to convert seawater into fresh water, all uses energy, right? So energy, water, food is intertwined in so many different ways. And let's look at how much they are affecting each other. So for we're talking about the energy uses, water uses, 78% was used for food production. But energy generation uses 16%. That's the second largest consumer for water. And that may be a little kind of surprising to some people. And if we lose, if we need more energy, we're gonna need more water. If the population continues to grow, we're gonna need more food. So why do I worry about that? Because, so I took these facts from a few reports. You can see the water demand is going to increase by 20 to 30%. The demand for food is going to increase by 50%. Demand of energy is going to increase by 25%. What's the common thing here? Increased needs, every single one of them. But your freshwater demand supply is going to be short by 40% in 7 years. It's very scary here. And you can easily see kind of a chain effect here. You have a climate crisis that's already reducing the amount of water we have. And yet we need more food to feed people. We need more energy to help us electrify our grid, but you're not going to have enough of that. And our municipal needs for water treatment, distribution, wastewater treatment, we're not going to have those resources. So that's a real problem. That's why we've been looking at the whole integrated system of food and energy water nexus. So here is kind of a framework that I took from the internet that talks about, how those three things work together and where are the different areas that we can look to help. So I don't have the solution for you here. If I have the solution, I'll be a billionaire today. But what's important here, my animation got messed up, is first understand the relationship between the three, not just qualitatively. We also need to understand quantitatively, how do they impact each other? So you can understand what kind of solution you can generate in order to gain what kind of effects, right? Then looking at solutions that are integrated management, when you try to solve one side of a problem, don't forget about the other two, and if that's going to impact the other two. And also a lot of times, you're not going to get the best of all three worlds. You're going to have to make trade-offs. So we need to understand where the trade-offs are. What can we live with? What can we not live with? So those are the important things that scientists are trying to figure out, engineers, and also trying to figure out practical ways, and also policymakers, right? The policies affect things a lot. When we demand water usage, when we demand fuel blends, when we demand, carbon emissions, what kind of trade-off we have to make. So all of those are important. Now, how do we leverage all these different energy to create a more sustainable future for ourselves? I'm just going to give a couple of examples. Floating solar. Has anybody heard about floating solar? So basically, we have limited, that's one thing I forgot to mention. Land about energy. Solar, wind, they all take up land, right? Even hydropower takes up land. So that's also competing. There's already some concerns about people in California where they're selling their farmland to solar farms, then how are you going to produce enough crops for people to eat, right? So when they're competing, we need to come up with innovative ideas to reduce the amount of land or water we use. So think about the reservoirs we have, all this surface of water. Can we use that for something else in addition to just the water storage and energy? So that's where floating solar comes in. So we have solar panels not standing on land or on top of buildings. They can go on surface of the water in the reservoir. So you combine that with a hydropower generation that can increase generation, but not increasing any utilization of land. So smart idea, right? So I love that. That's why I want to point that out. So not only people have tried to use hydropower reservoirs or any sort of clean reservoirs, they started using abandoned mines where you have all these toxic material on that big piece of land that nobody can use them anymore. And China actually built a huge solar farm on reclaimed mine reservoirs, which is, I thought it was pretty brilliant. And the cost of the floating solar has reduced over the years. And the capacity, because of that, the capacity you can see just skyrocketed in the last 6-7 years. Another slide of that. So here's the actual, I should have put this maybe on the first slide, it will be a lot more clear. So some people have run some ideas of how much you need to cover up the water surface in order to generate more energy. So it's somewhere around 3 to 4% of the water surface. If you can convert that to floating solar, you can virtually almost double the production of energy from the hydropower project. So there's a huge potential there. So look at all the benefits, reduce land use, and also these things, we talk about evaporation, right, just now because of the drought and the heat. When you cover the water surface with metals, you are actually shielding a lot of that evaporation. It's really a cool thing, right? It's a double effect. And also, fish actually like to live in the shade a little bit. So a lot of places, they actually combine fishery with floating solar. And that's really neat idea as well. So there's reduce the civil works because you don't need to construct those support systems for the solar panels, and reduce evaporation already talked about. And when the temperature is lower in the water, you improve the ecological benefits of the water and improve the water quality as well. So there's a lot of benefits related to this kind of setup. So I'm a big fan of this. So just to summarize, the role of hydropower in our future energy market, there's no one silver bullet to solve all the problems with energy or increasing energy needs or moving ourselves away from coal to renewable energy. As we get more wind and solar, the projection is by 2025, we're gonna get 15% by wind and solar. As a matter of fact, last year, 2022, it was already close to 12%. So we may even exceed that 15% by 2025. Then what? How do you replace the base load that's still provided by fossil fuel or nuclear? Those variable energies are not going to be able to serve that role. So I think personally, hydropower is really the best option for replacing that base load. And then of course, the storage, the ability to arbitrage, the ability to balance the energy storage, the energy generation is really great benefits that we need to take advantage of. And pump storage and battery, as I mentioned, has their own roles. We can't exclude one or the other. I think they both have some benefits in different scenarios. So we should use both to optimize the system and and react to the needs for different specific region and specific situation. There was a study that I heard, unfortunately I couldn't find the base information, but there was a study that was done several years ago in Pacific Northwest, where they did a few scenarios to say, what is the maximum installed capacity do I need in this region if I install wind and solar, projecting the energy demand by 2035, for example. And then they added pump storage in there, say, if I have pump storage in addition to wind and solar, what's the maximum capacity I need to meet energy demand? Surprisingly, once you add the pump storage, the required installed capacity came down substantially. Because when you build those energy projects, let's say you have a peak demand, but you have to overbuild the capacity to account for the variables in when the wind and solar are not maximizing its production, or worse yet, sometimes goes down to zero when you have cloudy days, when you have no wind days. So you have to overbuild the capacity to make sure that you can meet the peak demands when it happens. But when you have pump storage, you can shave that, very easily by storing the energy and then produce it when you need it. So that way you don't have to overbuild, because you already know you have the mechanism to provide that difference in the energy production. So that is another way to reduce the investment in energy and use that resources elsewhere, right? So this kind of concludes my presentation. This is a picture that I've kind of played in my brains for many years. And I asked my communications group to give me a picture with all of the renewable energies in one place. And they came up with this. I really love it. So we can have, floating solar, working with hydropower, and the water from the reservoir can be used to grow energy crops. And those go into a biorefinery that can produce biofuel to replace petroleum products. And we have wind farms nearby that can also take advantage of our transmission system. So that's my dream. Hopefully one day that will become true. So that's everything I have.
All right, thank you so much.
You're welcome.
I'm just going to turn the mics on in the room here, so you don't have to necessarily repeat the questions.
Okay.
Okay. Any questions in the room?
Go ahead.
You did mention that during generation power, some thermal generation. Can we?
Yeah.
Is it significant? And if it is, can we utilize that?
You mean the type of hydropower where I mentioned thermal?
Yes.
Yeah, I'm not quite familiar with that. I think that's a very, very small fraction of hydropower generation, if any. A lot of them are kind of in just a prototype experiment stage. In that whole category, the marine energy, a lot of them are in more experimental stage. Yeah.
Question online. What future do you see for small and micro hydro?
I think small and micro hydro has a lot of future. If you look at many different regions in Africa and those drought areas, for example, you just don't have the large resources available. And besides, when we talk about the Rhino River, you have much less influence, bad impacts to the environment. So that's the type of the hydro that most countries are looking at as more of a sustainable solution. And you're going to see much fewer of those impoundment storage type of hydro where you have to build large reservoirs, you have to move a lot of people, and there's a lot of geological implications that comes along with it, and socioeconomics issues come with it. So small hydro is going to be a much bigger trend going into the future. And especially in areas, and again, I'm going to bring up more remote areas in Africa, where you just don't have the infrastructure for transmission either. So even if you are able to build a large hydro, you have to basically rebuild the entire power grid to be able to transfer the electricity from one place to the other. When you don't have that, microgrids are going to be the best solution that can be implemented fast and more economically. And really, those small hydro doesn't produce that much electricity. If they can supply a whole village, that's the best. And they just need to be able to build a microgrid around that village. So that would actually be a really good solution.
And in addition to that, there is this microgrid idea in the United States also, where you can be more robust. You can isolate from a problem and generate locally, where small hydro really is the basis of that.
Yeah.
An economic standpoint, sense as to what the minimum capacity of a pump storage facility would be?
So there's a lot of different ideas that's been thrown around in terms of pump storage. Traditional ones you have seen are probably in the hundreds to 2,000 megawatt range. But again, those take a lot of upfront cost. The most recent pump storage in the US that's been built was a 40 megawatt pump storage in California. So that's probably the smallest one running currently that I'm aware of.
What capacity did it have in megawatt hours?
Megawatt hours, I don't have them. Oh, the storage.
Yeah.
I think it's the 40 megawatt is probably less than 8 hours. So the ones about, let's say, 500 to 1,000 megawatt could last somewhere around 60 to 72 hours, right? So 40 megawatt would be around 10% of that. Yeah, 48 hours.
I think it's a daily average of 8 hours.
Yeah,
There,
48 hours.
4 to 8, yes.
Yeah,
So it's when I say its capacity, not its instantaneous capacity, but overall capacity would have been 8 hours at 40 megawatts.
right. Now I have heard there were some projects under planning down to like about 5 megawatt pump storage projects. But I don't think that has been constructed yet. So 5 megawatt would be an hour or two, maybe. Yeah.
It could be long.
It depends.
I designed a small one.
Right.
It never got built.
Yeah. So I can't really say for sure.
Another question online. Has there been a cost comparison between pump storage versus battery storage for a large solar installation backup over a 10 to 20 year period when all the batteries would need to be replaced possibly more than once?
So I don't know if that kind of apples to apples comparison has been done. NREL, one of the DOE national labs, have been doing a study on pump storage valuation for years, for about 4 to 5 years. So they have published reports online. I haven't read the recent report. So there are a lot of variables in pump storage variation, as I mentioned earlier. It's very difficult to calculate the exact value when you are just a standby resource. What if something happened? And I've talked to many people over the years about a study like that, assuming like I call it avoided cost study, to look at a hypothetical disaster situation. What would be the damage that that could occur to the system? And then you assume you have a pump storage that can kick all the power back instantly, and then calculate the difference in that value. So I think that would, if that study is done, that would probably provide a pretty close answer to that question. But I haven't seen that study being done yet, and I don't have the money and capacity to do it myself. Should we ask?
Are there any pump storage sites that are under development in Wisconsin? It feels like there's several like candidate locations like along the Niagara Escarpment and the Great Lakes, or like the Mississippi River Valley or the Wisconsin River Valley, where there's large elevation differences near existing reservoirs. You know if there's any projects there?
I am not aware of any active ones that are being licensed or permitted. Wisconsin is still a relatively flat terrain. So it's normally not a kind of prime spot for any developers to look at least, right? Developers are looking at bigger projects where they can do great things. They can, you know, do big capacity. Now there is a pilot study, not a project itself, that's been looked at for underground pump storage in Minnesota. And that's a kind of a fast track project.
There's another one using abandoned mines here in Wisconsin. It's
Yeah.
just a study.
Yeah, most of them are very early phase. They haven't been even permitted, so it's just a concept.
All that is just being looked at commercial, industrial perspective. New capacity, as opposed to smaller distributions where it might be a community or project. More applicable than to be also utilize the energy locally, community oriented. There isn't any information on those in there, or is there?
Not anything that's in the process of, you know, being put through the licensing process because of the complication in the permitting process.
It'd be the same depending on, regardless of the scale of the project. I imagine there'd be more regulations on a bigger scale than a smaller
Right.
scale, but there's probably
Right.
still a lot in either.
There hasn't been a lot of optimization in the permitting process for pump storage, unfortunately. There has been some kind of simplification of the process for smaller traditional hydropower, like they call the conduit project. They are smaller than 5 megawatt. Then there are some waivers you can apply for. You don't have to go through some rigorous process. But in the pump storage world, I'm not aware of any sort of big initiative to simplify the process because it's more of a community oriented and a smaller capacity. So there's a lot that needs to be done on the federal side if they really want to encourage this.
Right. And then the last thing is more of a comment, but Raj says it should be mentioned that the disposal problem for solar and wind is likely more problematic compared to hydro as well. It's kind of a comparison.
Yeah, that's very true. And when I actually own a windmill at my house, there is no known process for recycling wind turbine. Even for solar, the percentage of recycling is still a pretty small fraction of all the materials. So, and for hydropower, there's not a lot you have to recycle unless you want to tear it down. Yeah, but you can keep rewinding the machine. The machines can last 60, 70 years or 100 years sometimes. Or you can actually upgrade an older machine to make it more efficient. So they can last a long, long time. Yeah.
I think we're out of time, but thank you so much for your presentation today.
Thanks, everyone. If you have any questions, I'll hang around for a few more minutes.